All right, so today we're going to get into Chapter 18, which is going to start talking about, in large part, enols and enolates, which still involves the carbonyl, but everything that we've been talking about up to this point in terms of the carbonyl, we've been talking about it functioning as an electrophile, right? So we've had nucleophiles attacking the carbon of the carbonyl, giving us alcohols and other things, right? I mean, we've been talking about those types of reactions quite a bit. However, the alpha carbon to a carbonyl, those hydrogens are acidic, and we can generate either enolates or enols at that position, which can function as nucleophiles. So we're kind of looking at the other side of the carbonyl. We've been focusing an awful lot on the carbonyl carbon itself, and now we're going to focus on the alpha carbon, which can do other types of chemistries, okay? And so it turns out that enols and enolates, we could have an entire graduate course that would cover an entire semester just on those topics. So what you're going to leave with is just the tip of the iceberg for enols and enolates, but you're going to leave with the meat of it, the fact that we can actually generate these things fairly easily and utilize them as nucleophiles in a variety of reactions. Okay? So as I mentioned, if we have a carbonyl, in this case we're just looking at a ketone, right? The carbon directly attached to that carbonyl is known as the alpha carbon. Obviously we can have more than one alpha carbon, right? You can have two, but in this case we're just looking at the one, and we can see that that hydrogen on that alpha carbon, we call that the alpha hydrogen. Just common nomenclature when we're talking, okay? Now that alpha hydrogen can move, if you will, to give an enol. What would we call that process? Going from a ketone to an enol like that. What was the name of that process? We've talked about it before. Started with a T. Tautomerization. That's right. So ketones tautomerize to enols. What's the favored form, the keto form or the enol form? The keto form. That's right. So 99.999% of most ketones, right, when you're looking at them in solution, you'll just see the ketone structure, not the enol structure. Now that can be altered, okay, and we'll talk a little bit about what can go into that. We can also remove the alpha hydrogen completely and end up with what's known as an enolate. And what you need to know is that enols and enolates have similar chemistry. How you generate an enol is different than how you generate an enolate, but the chemistry of both of those intermediates is fairly similar. And so it turns out that we can take an enol or an enolate and react them with a variety of electrophiles and make a new carbon electrophile bond. Now, if that electrophile happens to be something like an alkyl halide, we're forming a carbon-carbon bond, which is very, very important, right? We've learned a lot of ways now to make carbon-carbon bonds, and this is another way to do this. We can also, electrophiles can also be carbonyls, which would also form a carbon-carbon bond. They can also be halogens, which will make carbon-halogen bonds. So we're going to learn a lot of different electrophiles that can react with these intermediates to make new molecules. Okay? So the take-home here is that enols and enolates are good what? They're pretty good nucleophiles. And so anytime we have a nucleophile, we look for the electrophile reacting partner, right? Okay, so good. Now, if we take a ketone, for example, in this case cyclohexanone, and again we've got two alpha carbons, we're just looking at one of them, we can set up an equilibrium where we have an enol. That enol will almost always be less than 1% of the mixture. Keto-enol tautomerization occurs in solution, but that enol form is very, very low in concentration, okay? About less than 1% for the most part. And again, you can shift that equilibrium by doing some things that we'll talk about later, okay? And it turns out that the carbon-oxygen double bond is stronger than the carbon-carbon double bond, and that's why the equilibrium lies to the left. It's all about bond strength, okay? So at this point in this semester, we're in April, right? We're at the home stretch of your experience in Organic 1 and Organic 2, right? And at this point, I'm hopeful that what you have is a sense of where equilibria lie. You have a sense of what nucleophiles and electrophiles do, because this is going to be a very, very important stuff for you when you go on and get into biochemistry or physical chemistry or your polymer chemistry class, where you're talking about polymer organic. You're going to need to have a sense qualitatively of where equilibria lie. Okay? So hopefully at this point you have a better understanding of that. Now if you take a molecule like this one on the right, this ketone, notice we have two alpha carbons. Are they identical? Are those two alpha carbons identical? No, they are not. So technically they should have labeled them alpha and alpha prime, right? Because they are different. But we can imagine the methyl group alpha, right, tautomerizing to give this enol, and we can also imagine this alpha hydrogen tautomerizing to give this enol. Now this mixture would be less than 1% of the overall mixture if we were to look at this ketone by NMR. But which of these two enols would be there in greatest abundance, comparing the two enols? Would it be 50-50? Okay, so you're saying the first one because it has more hydrogens. Okay, that's a rational argument. And then I heard another argument. What was the other argument? More substituted what? Double bonds, that's right. And so we have just made the argument that I was hoping we would get into about kinetic versus thermodynamic. Harrison is absolutely correct. If this was a kinetic phenomenon, that the first one would be because there's more hydrogens, right? But is this a kinetic or a thermodynamic phenomenon? If we're talking about equilibria, we're talking about thermodynamics, right? So under thermodynamic conditions, we would expect this enol to actually be the major component of these enols because, as Gabby said, what did you say? It's the more substituted double bond. And remember, our alkene stability, the more substitution we had, the more stable. Exactly the same argument here. Okay? But both of those arguments are rational at the very face, right? I mean, your argument was not an irrational argument. It's just we were not under kinetic conditions, we're under thermodynamic conditions. And we know that anytime we're dealing with equilibrium, we're talking about thermodynamics, right? So we had to look at the enol that would be the thermodynamically most stable, and that's the one that's the most substituted. Very good. Other things, there are carbonyl-containing molecules that actually favor the enol form, okay? If we look at 2,4-pentane-dione, which is what we call a beta dicarbonyl compound, alpha beta, so it's a dicarbonyl, but this would be one, alpha beta, so that's why we call it a beta dicarbonyl. If Gabby was to take this molecule, put it in an NMR tube, and go to our NMR, what she would find is that about 24% of it would be as this beta dicarbonyl compound, but over 3/4 of it would be as the enol. This is an example where the enol form is actually more stable than the carbonyl form. What do you think that is, Sarah? It is more stable. It is a good answer. And why is it more stable? Hydrogen bonding. That's exactly right. Not only hydrogen bonding, that's one part. What's the second part? Pardon? Conjugation. That's exactly right. If we look at the carbon-carbon double bond, we notice that that's in conjugation with the carbonyl, so we can draw resonance structures, right? Can I draw resonance structures? No, it's an isolated carbonyl and an isolated carbonyl, but now it's an alpha-beta unsaturated carbonyl, as we call it, and we can draw resonance structures between these four atoms. Also, the hydrogen bond forms a nice six-membered ring, and what do we know about six-membered rings? They're fairly stable, right? So we have a fairly stable six-membered ring. We have a conjugated system. So the equilibrium lies to the right. Okay? So there are enols that are very, very stable. That's an example. Can anybody get, yes?
Can you explain again why you can't draw resonance structures?
You can draw resonance structures, but you can't draw resonance structures across all the atoms. So for example, I could draw a resonance structure like that, right? But that's a very minor contributor to the overall resonance hybrid. Whereas here we have a lot of delocalization, and I can actually draw some fairly stable resonance structures that contribute nicely to the overall resonance hybrid. Okay? So, can anybody give me another example of an enol that's extremely stable? That's right, phenol. If Sarah was to take phenol, put it in an NMR tube, and go get an NMR, she would only see phenol. She would not see the ketotautomer. Tell me why. Why does this not undergo keto-enol tautomerization? Why is it all at the phenol? That's exactly right. So we have an aromatic ring in the phenol form. Do we have that in the keto form? Why is this not aromatic? It's not completely conjugated. That's exactly right. Would it be planar? It'd be pretty close to planar because of all the conjugation that you have here. It'll be a little puckered, okay? But it's not going to satisfy Huckel's rule, right? It's not completely conjugated. It's not aromatic. But the enol form of this ketone, which is phenol, is aromatic and extremely stable, okay? So for a typical ketone, the keto form is favored. But there are situations where the enol form is favored. So you want to think about things like hydrogen bonding, resonance, conjugation, aromaticity. Those types of things can actually favor the enol forms quite substantially, as you can see from these slides. Okay? So now let's talk about the mechanism of enol formation in acid and base. And let's just use a ketone. So let's take, I don't know, butanone, and let's look at how we can make an enol from the most substituted alpha carbon, okay, the one that I've drawn there. And we know that this is an equilibrium process, so that would be my enol tautomer. This can be promoted in both acid and basic conditions. Which one do you want to start with, acid or base? Acid. Let's start with acid. So, if we take this and place it in acid, okay, I'm just going to use a generic acid. Tell me how acid favors the formation of the enolate. How does that, or the enol, excuse me, how does that happen? What are the steps in the mechanism? The hydrogen attack the oxygen. Ah, the oxygen attacks the hydrogen, and why is that? That's right, because we've got the lone pair of electrons. Yeah, the atom's right, right? So we know that the oxygen of the carbonyl is a Lewis what? It's a Lewis base. It's an electron pair donor. And what happens to the formal charge on this oxygen? It becomes positive. That's right. Now, it's acid catalyzed. So what happens next in the second step? H leaves just by itself? You're right, we have to remove the H, but how do we do that? All right, that's true. Now you said push all. Tell me, describe. Be a little more descriptive, please. Uh-huh. And that gives me my product, right? So under acidic conditions, we can generate enols quite easily. Okay? Through this process. Everybody got that? You want to take a picture? No? It's in your book. We can also promote enol formation under basic conditions. So let's say sodium hydroxide. How does that happen? How do I get an enol with sodium hydroxide and a ketone? So I've got sodium hydroxide, we've got water around, right? So what's going to happen? How am I going to get an enol under these conditions? Now what happens? It's base catalyzed. So we got to get our base back, right? And so that's how we get our base back. So the alkoxide, which is actually an enolate, reacts with water to form the enol. Okay? So we can promote the formation of enols and in the presence of both acid and base. Okay? Now, what kind of base am I using here? A really strong base or a fairly weak base? Does it? To completely abstract the hydrogen 100%, you're absolutely correct. But here, this is all equilibria, right? Do I have to completely generate the enol? No. Okay? So actually, for the formation of the enol, you need a fairly weak base, something like sodium hydroxide, potassium hydroxide, or something. If we used an extremely strong base, we would actually not get an enol, we would get an enolate. Okay? And so we'll talk more about that in just a minute. Okay. So enolates are formed when we have a really strong base reacting with the alpha hydrogen of the carbonyl. Very simple mechanism, right? Removes the acidic hydrogen. You end up with the enolate where the negative charge is on carbon. We can draw a resonance structure putting the negative charge on oxygen. It is a resonance stabilized enolate anion. Which one of these resonance structures, the one on the left where the negative charge is on carbon or the one on the right where the negative charge is on oxygen, is the major contributor to the overall resonance hybrid? I saw some thumbs go this way, right? So to the right. Why is that? Pardon? And why? More electronegative. So oxygen is better at handling that negative charge than is carbon, right? And so we expect that the structure on the right to be the major contributor. And in fact, if you were to do this reaction in an NMR tube and go run the NMR, you won't see any of this. The concentration of this resonance structure is non-existent. It's actually, this is the structure. However, the fact is that that carbon with the negative charge, even though it's a minor contributor to the resonance hybrid, it's important because what happened on that first slide when we took enols or enolates and reacted them with an electrophile? Did the electrophile react with the oxygen or the carbon? It reacted with the carbon, which suggests that the resonance structure, the minor resonance structure on the left, is what's doing all the chemistry. Can anybody explain that to me? Why is it that an electrophile would prefer, quote unquote, to react at the carbon and not the oxygen, even though oxygen bears the negative charge in the enolate? got it. So the carbon atom, being less electronegative, is more willing to share its negative charge and function as a nucleophile. That's oversimplified, but that's exactly what's going on, right? So the oxygen atom bearing the negative charge, does it hold on to that negative charge strongly or weakly? Strongly. And so the oxygen is actually not the better nucleophile. Okay? Remember that as we go from left to right in a period, nucleophilicity increases or decreases? Decreases, right? So carbon is a better nucleophile than oxygen, right? So those trends are starting to come back, right? You need to have committed to memory some pKa ranges. You do not need to have all of them that I'm going to show you here committed to memory, okay? But you all know that an alkane has a pKa of about 50. That makes it a weak acid or a strong acid? Very, very weak. But as we start to introduce some oxygens, right, like carbonyls, we notice that the pKa's get much better, right? And so if we look at a typical ketone, the ketone has a pKa of about 19 to 20. So relative to the alkane, it's a stronger acid or a weaker acid? Much stronger, right? And the reason is because the conjugate base is stabilized, right? We always look at that conjugate base to figure out acids, right? So if we're looking at the alkane, the conjugate base is the carbanion. Can I do any kind of resonance delocalization or anything of that? Absolutely not, right? It's not very stable. However, in the enolate form, it's stabilized by what factors? Resonance, putting the negative charge on an oxygen as opposed to a carbon, right? So the element effect also comes into play with that, okay? So typically ketones are going to be somewhere around 19 to 20, okay, depending on what else is attached to them. We can also generate enolates of other carbonyl-containing molecules. Esters, nitriles, although nitriles technically aren't carbonyl-containing, remember we throw them all into that same category, right? And so we can take an ester, and the alpha hydrogens on the ester can be removed under basic conditions to give a resonance stabilized enolate. We just call them enolates of esters, not enolates of ketones. We can do the same thing for nitriles. The alpha hydrogen can be removed, and we can end up with enolates. Technically, you want to call them a carbanion because the enolate has to have an oxygen, but very similar types of chemistry. Okay. Where do you think the pKa of an ester would be, the alpha hydrogens? Would they be less acidic or more acidic than a ketone? Actually, they're less acidic. Ketones are actually quite acidic. They're about 19 to 20. The alpha hydrogens on an ester are about 24, 25, 26, somewhere in that range. Does that make sense right off the top of your, just looking at it? Why not? Why does that not seem to make sense to you? I can't draw more resonance structures. It does have to do with resonance structures. So what I want you to do as a take-home assignment to bring back on Friday is to draw a ketone and the alpha hydrogens to a ketone, show the formation of the enolate, then I want you to do the same thing with the ester, and I want you to come up with a rational argument for why ketones are more acidic than esters. And I'll just tell you, it has to do with resonance. Okay, so think about that. But you need to come up with your own explanation for why that observation is there. Okay. So if we look at the table that you need to kind of have committed to memory. Now, do I care that you have it exactly committed to memory? No. You need to know the rough ranges. Okay? So the alpha hydrogens of an amide have a pK of around 30. The alpha hydrogens of a nitrile, about 25. The alpha hydrogens of an ester, like I just mentioned, around 25. A ketone, around 19. Right? We can clearly see, based on the data presented, that ketones are more acidic than esters. Aldehydes are slightly more acidic than ketones. They have a pK of around 17. These 1,3 diesters, or these beta esters, if you will, okay? They have a pKa of around 13. That's starting to get fairly acidic, right? What's the pKa of water? Around 16, right? So these have a pKa below that of water, so hydroxide can readily deprotonate these. Can hydroxide readily deprotonate an ester? No. A ketone? No. Right? But a 1,3 diester it can. A 1,3 dinitrile? 11. A beta keto ester, where you have a ketone and an ester? Just under 11. Right? These hydrogens are actually quite acidic. And these beta diketones that we talked about earlier, they have a pK of about 9. Okay? Why is it that everything over here on the right has a pKa less than water? It is. That's true. What else? What's the difference between the stuff on the right and the stuff on the left? Take the diester and the ester, for example. You've got double of them. I can draw more resonance structures, right? So if I remove this hydrogen, I can draw a resonance structure that puts the negative charge on this oxygen or on that oxygen, right? So I can draw more resonance structures for this structure than I can for that structure. And it has a big effect. The way that I like to think about it is that I've got this negative charge and I've got two groups that can pull the electrons away by resonance, right? And that stabilizes it quite considerably, right? So if we consider that the ester is 25 and we take the diester to be 13, that's a lot of orders of magnitude. That's 12 orders of magnitude difference. 12 orders of magnitude, remember that's 10 to the 12th, that's a lot of zeros, right? That's big, okay? So that's a huge difference in stability of those anions, okay? You also are going to need to know something about different types of bases. You're just going to have this committed to memory, okay? You need to know that the pKa of water is around 16, right? And the conjugate base, of course, would be sodium hydroxide, right? So if I took a typical ketone, which has a pK of around 19 to 20, we're using 20 here for good round numbers, and I react it with hydroxide, I'm going to get less than 1% of the enolate. If you go through and do the math, you'll find that it's much, much less than 1%, because the pKa difference is so great, right? 16 and 20, that's 4 orders of magnitude difference. So the equilibrium does not lie to the right, it lies to the left, right? This is all getting back to that JChem Ed paper I gave you early on about how we can use pKa to determine the position of an equilibrium. If I use an alkoxide, okay, we've used these in the Williamson ether synthesis before. They're good nucleophiles. They're reasonably good bases, but the pKa is about that of water, just a little bit higher. Again, not a strong enough base to completely deprotonate the alpha hydrogen on a ketone. So the equilibrium does not lie to the right, it lies to the left, right? So less than 1% of the enolate. If, however, we use potassium tert butoxide, okay, what did we learn about potassium tert butoxide? It's a stronger base by about 2 orders of magnitude because it has a pK of 18. Is it a nucleophile? No. All nucleophiles are bases, but not all bases are nucleophiles, and it's too bulky. Why is it a stronger base than hydroxide or a typical alkoxide? Not resonance here. We can't draw resonance structures. But what are alkyl groups? Are they electron donating or electron withdrawing? They're electron donating, right? And so we got these three methyl groups that are donating electrons, making that oxygen anion more electron rich, if you will. And so more reactive by about 2 orders of magnitude. So even with this, we're getting closer to that 20 number, right? And so you can get about 1 to 10%, more or less, depending on what kind of carbonyl compound you're using, if it's a ketone or an aldehyde, et cetera, okay? Now, sodium hydride, hydrogen has a pKa of 35. 35 is how many orders of magnitude greater than 20? 15. 15 orders of magnitude greater. So does the equilibrium lie to the left or to the right? To the right, and so far to the right that we consider it to be completion. So if Katie was to take acetone, for example, and drip it into a flask containing sodium hydride, she would completely convert the acetone into the enolate, 100%, because of the pKa difference, okay? So the pKa of sodium hydride is around 35. This one that you see here is known as lithium diisopropyl amide. Amide, I shouldn't say amide, amide, but it's spelled the same. LDA. Lithium diisopropyl amide. What can you tell me about that base? It is bulky, so it's not a good nucleophile. And it's quite basic. It has a pK of around 40, right? So when Sarah reacts her carbonyl compound with that base, she gets complete conversion to the enolate. Okay? You're going to need to know LDA by memory. And you're going to need to know that it is a strong non-nucleophilic base that can convert carbonyl-containing compounds completely to the enolate. But wait a second, we've got sodium hydride that does exactly the same thing. Why do I need 2 bases when one seems like it will work just fine? Can anybody tell me what the big difference is between LDA and sodium hydride? Pardon? That will come as a result later. Okay, we've got the negative charge on nitrogen versus the negative charge on hydrogen. That's a big difference. What else is a difference?
One's organic and one's soluble in water.
That's right. One's organic. Well, soluble, it reacts with water, but it is a salt. So if Nate was to come into the lab and take sodium hydride and try to use it as a base in a typical organic solvent, would it be soluble? Do salts typically dissolve in organic solvents? No. Typically they do not, right? That is an inorganic salt, sodium hydride. It just forms a slurry. It will work, okay? But what about lithium diisopropyl amide? It's a salt, but is it going to be soluble in the typical organic solvents? And why? Why will that salt be soluble in organic solvents, whereas sodium hydride is not? It's got the alkyl groups. That's exactly right. So it will be soluble in organic solvents. And it turns out that this solubility difference makes a big difference in the selectivity of how we generate enols and enolates, which we'll talk about later. So Sam was kind of foreshadowing some of what's to come. Okay. I want you to have a feel for the position of the equilibrium. I want you to know, should it lie to the left or to the right? For weak bases, it's going to lie to the left, and for the stronger bases, it's going to lie to the right. Okay, good. So, if we were to generate an enolate, remember we can draw 2 resonance forms for the enolate. So let's assume we take a ketone, we react it with a strong enough base that can generate completely the enolate. What 2 bases might we use for that? LDA or sodium hydride, right? Either one of those, in theory, would work just fine. We could imagine the electrophile reacting with the oxygen to give a new oxygen electrophile bond, or we can imagine that the carbon atom bearing the negative charge in this resonance structure reacts with the electrophile to make a new carbon electrophile bond. The top one is the preferred pathway because carbon is a better nucleophile than oxygen. Okay? Now, if we were in my graduate level class, we would talk about reagents that can actually react with the oxygen, and we would talk about reagents that will react with the carbon. Okay? There are ways to play with Mother Nature. Okay? For the purposes of this class, that top preferred pathway is going to be the correct answer. We're only going to be talking about the chemistry at the alpha carbon, not the chemistry of the oxygen anion. Okay? If you want to know more about how you can do enolate chemistry where you react with the oxygen, that's more of a graduate level course. Okay? But all of the reasons that we discussed for why the carbon reacts preferentially are true. Okay? They are true. So, we know that the carbon is a better nucleophile, but if looking at those products, what's another thing that you can tell me for why the top pathway is preferred over the bottom one? What do we know about the bond strength between a carbon-oxygen double bond and a carbon-carbon double bond? That's right. So that's another piece of evidence for why this top pathway is the preferred pathway. Can this bottom chemistry occur? You bet. But you have to have a special class of electrophiles that we say are oxyphilic. They like to react with oxygen, and that's beyond the scope of this particular course. However, you will learn it as you move up the chain in chemistry courses, polymer chemistry courses. They'll probably talk about it. Okay? But that top preferred pathway is the typical pathway that we undergo. Okay? Now let's imagine that Jamie comes into the lab and she wants to take 2-methylcyclohexanone and she wants to generate an enolate. She has a problem because both alpha carbons are identical or non-identical. They are non-identical. So we can imagine generating two different enolates, right? If she was to remove one of the secondary hydrogens, she would generate this enolate. If she was to remove the tertiary hydrogen, she would generate this enolate. Okay? Now, if she just starts off and doesn't think about which base to use, she could get one or the other, or she might get a mixture of both. Do you think that that's going to be particularly useful? No. We need to have conditions by which we generate the top enolate, so we can do chemistry on that carbon, or the bottom enolate, so we can do chemistry on that carbon. Okay? This top one is known as the kinetic enolate. Can anybody tell me why it's called the kinetic enolate? Harrison, this gets to what you were talking about earlier. Why is the top one known as the kinetic enolate? That's right. So if I'm a base, I've got twice the opportunity to abstract a hydrogen from that alpha carbon than I do the other alpha carbon, right? So it should happen faster, correct? It's less bulky there, right? So we can generate a kinetic enolate. It's formed faster. And why is this one called the thermodynamic? What's more stable? Why is it more stable? More substituted. The Gaby rule, right? So we have the thermodynamic enolate and we have the kinetic enolate. This is where life gets complicated for you. You're going to need to know what conditions generate the kinetic enolate, and you're going to need to know what conditions generate the thermodynamic enolate. Very similar. Very, very similar. Okay? So when we were generating kinetic in the past with this diene stuff, as you called it, right? What kind of conditions were we using? It was really cold, right? So if Harrison wants to generate the kinetic enolate. He's probably going to run this reaction at room temperature? About -80, -78. He's going to use really cold conditions to get that enolate to be the kinetic enolate. And if he wanted to generate the thermodynamic enolate, what might he do? Run it at higher temperature, maybe room temperature, right? So that's right. We're going to be talking about ways in which we can do this. Yes, Jamie?
Okay, so like in the other one, the kinetic product always formed first. Is
The kinetic product always forms first.
Okay, so in this one it doesn't.
But to get the thermodynamic enolate, you have to give it conditions by which it equilibrates to the more thermodynamically stable. That's always true. So, Jamie wants to come in and generate the kinetic enolate from this particular ketone. You're going to have a couple of conditions, and you need to know these. You need a strong non-nucleophilic base. Your go-to in this particular reaction is LDA. Are there other bases that will work? Yes. But for the purposes of this class, your go-to base in this particular reaction is lithium diisopropylamide. Okay? You need a polar aprotic solvent. THF is your go-to. What other polar aprotic solvents did we talk about that could substitute for THF? Got to pick one that won't react. DMSO is another possibility. Turns out you can't use DMSO because it freezes at -78. It kind of sucks. But it is another polar aprotic solvent that, at least on paper, could work. And you're going to need really cold temperatures, about -80. Okay? So when Maggie goes into the lab and she goes, I've got a ketone that's unsymmetrical and I want to generate the kinetic, she knows she needs to use low temperature, she needs to use a polar aprotic solvent, and she needs to use a really strong non-nucleophilic base. That's what she has to do, and that will generate the kinetic enolate as the major product. And by major, I mean 99 point whatever. It's usually very selective, getting to what Sam was talking about, selectivity. Okay? What would happen if, let's say, Gabby was running this reaction and she got it all set up and she generated the major kinetic enolate and she's got it in, a cold bath that's at -78, and she went, oh, well, it's time for lunch. I'm going to go to lunch for a couple hours, Dr. Masterson, I'll be back. And the bath started to warm up to room temperature. What would happen? It would equilibrate to the more stable thermodynamic product. Okay? So the kinetic enolate is generated very, very quickly at low temperature, and we need to use it very, very quickly. Okay? Because if it warms up, it will equilibrate to the thermodynamic enolate. Okay? So very, very important that you keep that in mind. To generate the thermodynamic enolate, we need a strong base, but not as strong as for the kinetic. We need a polar protic solvent, and we need room temperature or greater. Okay? So for example, Jamie takes this ketone, she's using alcohol as the solvent, ethanol, and she's using the salt of the alcohol, sodium ethoxide, at room temperature. She's going to generate the thermodynamic enolate. What percentage is this thermodynamic enolate going to be? Does the equilibrium lie to the left or to the right here? Before, to generate the kinetic, I told you that the equilibrium lied completely to the right, correct? Where does the equilibrium lie here? The ketone has a pK of around 19 to 20. The alkoxide has a pK of around, chance? Where's the pK of the alkoxide approximately? About 16. So is the equilibrium going to lie to the right or to the left? To the left. So we're going to have the enolate and its conjugate acid in solution at the same time. And anytime you have a situation like that, you will always generate the thermodynamic enolate. Okay? And so you'll get the thermodynamic enolate as the major enolate that you can do chemistry on at this carbon. Okay? So if I want to generate the kinetic, what are the three rules? Low temp, polar aprotic, strong, nonnucleophilic base. And your go-to is LDA. So here's something that I want you to think about, and we'll stop today. Let's take that ketone that's unsymmetrical, the methylcyclohexanone, and let's look at something. If Brienne comes in and reacts this at low temperature in THF, polar aprotic solvent, and she uses LDA as the base, we're going to get what kind of enolate? The kinetic, right? And if Jamie comes in and runs the reaction at minus 78 degrees, she uses THF, but she uses sodium hydride, what do you think we'll get? We do, but would you have predicted that? Remember, sodium hydride has a pKa of 35, right? It's a really strong non-nucleophilic base. But yet, we get the thermodynamic enolate as the major product. Which seems to counter everything that I just told you. So I want you also for Friday to explain this. Take a picture of it. I want you to explain why in the top example we get the kinetic enolate, and in the bottom example we get the thermodynamic enolate. Even though the bottom example fulfills all of the requirements for a kinetic enolate that I've told you about. So, what must the difference be? Must be something to do with the base. I want you to think about that. We'll talk more about it on Friday.